In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the epsilon delta language. Now, in this lecture, we will look at the second derivative of function and how it is related to a geometric property called concavity of the corresponding function. All right, so first let's see how we define the second derivative and other higher order derivatives. All right, so suppose we have a function f, which is continuous and differentiable on the open interval AB. Now, because if it's differentiable, then we have the derivative function f derivative. The point is, if this function is also differentiable, then we can take the derivative again. So we take the derivative of the derivative, and we get something called second derivative, and this is how we represent the second derivative. We can use the double prime, or we can put a 2 with a bracket here. So this is the second way to define the to represent the second derivative, or we can write things like this. Okay, so these are three different ways to represent the same thing, which is the second derivative of function. All right, so what's second derivative? Second derivative is the derivative of the first derivative. For example, let's look at some simple cases. If I have fx is x squared, right? Okay, so then if I take a derivative, then I get 2x. Now, if I take the derivative again, so the second derivative will just be, I take the derivative of the derivative, so which is the derivative of 2x, that's 2. All right, so the second derivative of x squared is just 2. Let's look at another example. If I have fx, say equals sine x, right? Then if I take the one derivative, the first order, this we know is cosine x. Then what's the second derivative? Second derivative is I take the derivative again, the derivative of the first derivative, right? So we get, okay, so we just get this negative sine x. So the point is for the sine x, the second derivative is the negative, the opposite of the original function. All right, now in the same way, we can also define higher order derivatives, right? By keep taking derivatives. For example, if I take the derivative of the second derivative, then I get the third derivative. So these are three different ways to represent the same thing, the third derivative. And in general, if I keep taking derivative, right, so if I use this to represent the nth derivative of f, which is the derivative of the n-1's derivative, right? Just keep taking derivatives. Right, for example, okay, what's the fx? Say it's x cubed, right? For example, x cubed. Then the first derivative will just be 3x squared. And if I take the second derivative, will be 6x, right? I take the derivative again, will give me 6, right? And then you say, okay, what about fx is sine x, right? So we already know the derivative of this is just cosine x. And the second derivative, you just take the derivative again. The derivative of cosine x is negative sine x, we just did. And if you look at the third derivative, right, you should look at the third derivative, then will be negative cosine x, right? All right, so you just keep taking derivatives, and this will give you, suppose you are able to do that, then they just give you all the high order derivatives of the given function. Now, compared to other high order derivatives, the second derivative is more important because it has a clear and important physical meaning. It represents the instantaneous acceleration. All right, so here's the basic setup. Suppose, let's say this is the x-axis, right? And then we have a particle that is moving, right? So here, this is a particle that's moving along the x-axis. Okay, now I say, for convenience, you say this is the origin. And here, this guy is this moving particle. Now we record the position of the particle at a time t, right? And then we say, okay, then this will just be st, is the position. Now st could be positive or negative, represents it on the, well, depends on whether it's on the left or it is on the right, right? Okay, right, so after we have the position function st, we know if you take a derivative, this is the rate of change of the position, and that's we know at the from the first lecture, this is the velocity. This is the velocity. Derivative is the velocity. Now, if I take the derivative of the velocity, which is second derivative of the position, this represents the rate of change of the velocity. And that in physics, we know it's called the instantaneous acceleration. So velocity is the rate of change of the position. And acceleration is the rate of change of the velocity. That's the second derivative of the position. Okay, so that's why second derivative is important, because of the Newton's law of second motion, right? Remember what is the, recall what is Newton's second law of motion, right? It says, okay, the force, the mass, right? So this is the mass times the acceleration. This is acceleration equals the F, right? F equals the mass times the acceleration. So that's why in the modeling, the second derivative is very important, like the first derivative, because very often you have the scenario to apply the Newton's second law of motion. All right, now let's look at a math problem from a past AP, calculus AB exam. It says, okay, here we have a particle, it's the velocity. So here what we know is the velocity, not the position, the velocity given by this. And we find, based on this piece of information, we want to find the maximum acceleration. All right, okay, so we know the acceleration, right? Let's do it. So we know the acceleration. Let's say I use AT to represent the acceleration at time t, instantaneous acceleration. Now, acceleration, just the rate of change of the velocity. So we just take the derivative of this one, right? So we get 3t squared minus 6t and plus 12t. Now we want to find, okay, so we just want to find the absolute maximum value, maximum value at this interval, right? On this closed interval, which is 0, 3. This is a quadratic function, right? Okay, so we can have, we say, all right, so I just want to find, let's say, this function, which is the ft. Now, we want to find the absolute maximum value. There are two ways, right? One way is, okay, so method one, we just use the algorithm. So what do we do? Okay, so first of all, we find the critical number, right? And I take the f derivative of this, you get 6t minus 6 equals 0, so I get t equals 1. This is the critical number, which is indeed between 0 and 3. Now step 2, okay, so this is our step 1, and step 2, we just evaluate all those numbers, evaluate the numbers and the end points, right? Okay, so I calculate f1, which equals 3 minus 6 plus 12, this is 9. And then I evaluate endpoints, which means 0 and 3, right? So f0 will be just 12. Now let's calculate f3. So f3 will be 27 minus 18 and plus 12, right? That's what we have. Okay, so now we get 21. All right, so now you compare the three numbers. You compare 9, and this is 12, and this is 21, and then obviously you just get 21 is the absolute maximum value. Or we can also use, because this is a quadratic function, right? So okay, if it's a quadratic function, you don't have to really use calculus, right? Okay, so if a quadratic function, so method two, no calculus. Right? No calculus. So what do we do is, okay, well, so I have, this is ft equals 3t squared minus 6t plus 12. I can pull the 3 out. This is t squared minus 2t plus 4. And then what we can do is, okay, how we find the maximum value of quadratic function? Let's complete the square, right? So this is plus 3, right? So this is plus 3. And then if you draw the graph, you see, okay, the graph of the function will be, this is 0, this is 1. Now we'll care about the 3, right? Okay, so now then if you draw the graph here will be the, so this is the graph, right? So this is the graph. This is the axis of symmetry. Here, this is the minimum value, which is 9, right? And then because obviously this is 1 and this is 2, and we know 3 is the maximum value, right? If you plug 3 here, you get 3 times 2 squared plus 3, and you just get the same thing, right? You just get the same thing, which is 21. Okay. All right, now let's look at important property of function, which is called concavity. And there are 2 kinds of concavity. One is concave up, and the other one is concave down. All right, so first let's do a concave up. Okay, let's look at the graph of the function. So this is concave up. Let's look at this, concave up. When you look at the graph of the function, you see what you do is, if I look at any point, for example, if I look at this point, right? So if I draw the tangent line, and you find that the whole graph is above it, well, except this touching point. And again, you look at arbitrary one, look at this. Okay, if I draw the tangent line, again, the whole graph is above the tangent line. And if I draw, okay, if I draw a tangent line here, again, the whole graph is above the tangent line, well, except this touching point. And also you see, if you go along the graph, right? So if you go along the graph, and the slope is increasing, the slope is increasing as x increases, right? All right, so here, so this we call concave up, and from here, as I said, analytically, you will find the derivative is, which is the slope, right? So this is the slope. The derivative is increasing. Okay, so this is one feature we'll get. All right, so the derivative is increasing. And as we said before, if increase function, that means the derivative of derivative, right? So we say, okay, a function increasing means the derivative is not negative, right? So we get, okay, so this means the second derivative is not negative. Right? If you have a concave up, well, on that portion, the second derivative is it's not negative. A special example is, right, a simple example is just look at the function y equals x squared. So this guy is concave up, right? So if you look at the derivatives, if you look at the tangent line, the whole graph is always above it, right? Okay, another one is concave down. This is concave down. So if you look at that, that's the graph of concave down here too. You see, for a situation like that, if any point, if you draw a tangent line, you see, okay, the whole graph is below it. And if you draw a tangent line, the whole graph is below it. And if you draw a tangent line here, the graph is also below it. But meanwhile, you see, if you go along the graph as x increases, the slope, okay, so you get the slope is decreasing. Right? So you get the slope is decreasing, and that means the derivative decreasing. Right? Okay, so then you get analytically for the concave down case, you get this derivative. This one is decreasing, and that means the derivative of this one, which is second derivative, right? The derivative, first derivative, this is non-negative. This is non-positive. All right. Well, a typical function is you just look at negative x squared, right? So this one is a simple example of its concave down. It's concave down. All right. When you look at this analytic feature, you see this basically provides a way to tell whether function is concave up or concave down. More precise speaking, we have this. So here's the subtle thing here. Well, if I use second derivative, we find the concavity test. It says, all right, suppose the function is the second derivative exists. This we also called is twice differentiable. Okay. Suppose I know the function is twice differentiable. Okay. When I say it's twice differential means the first order and the second order derivatives, they all exist. All right, and then suppose I know the second derivative is positive from AB, then I can get the f is concave up. If the second derivative is negative, then I can get the function is concave down, right? For example, if you look at fx equals x squared, so this is simple 1. You look at the second derivative, we know this is 2, which is positive. The function, as we know, it's concave up. If you look at x, negative square, take this is negative 2, which is less than 0. So as we know, the function is concave down. So it is consistent. Now, we are going to prove this. Okay, so I'm going to prove this. I will just do for 1 and 2 is similar. Okay, let's prove 1. Prove this one. All right. So what do I want to show? All right, so here we have a function, right? So this is a function. Here, this is a and this is b, this is x and this is y. Now we know the second derivative, right? We know the second derivative in this interval. This one is positive. All right. What we want to verify is, suppose I just look at the tangent line, right? So I say, okay, look at tangent line. This is point x0. This is my function, y equals to fx. Then I look at the equation of the tangent line, which is a linear function, which we know is fx0 plus the slope. And the slope is the derivative and times x minus x0. Okay, so we want to show it's above it, right? So we want to show it's above, the graph is above this tangent line. So that means we want to verify, is it true the fx is bigger than this lx if x is not equivalent to x0. Now x0 is the touching point where they coincide, right? So that's what we need to verify. In other words, if I let gx equals or equivalently the fx minus lx, right? And then the question is it true that gx is positive? If the gx is positive, if the x is not equal to x0, right? So that's what we need to prove. The other thing, what can we say about the gx? Let's look at two things. So number one, I know that gx0 equals 0, right? And number two, if I take the derivative of this, will be the derivative of f0 minus the derivative. Look at what's the derivative of this. It's a linear function, so it's just the slope, Okay, minus fx0, which is 0. Now, what's the second derivative of this? What's the second derivative of the function in the whole interval? Okay, so this is just the second derivative of fx. All right, so the second derivative of this linear function, because it's a linear function, the second derivative would just be 0, right? Constant 0, fx, and we know this is positive. All right, now we have a function. The function is, the derivative is 0 at this point, and the second derivative is always positive. Can we conclude the function actually is, it's always positive when it's away from the point x0? The answer is yes. Okay, let's look at a general statement. Suppose I have a function which is gx, and the function is twice differentiable. Okay, now I have a point which is x0, and we know the derivative of g at this point is 0, so it's a critical number. And here's the conclusion. Suppose I know the derivative, the second derivative is always positive in this AB. Let's first focus on this, and then this will tell us the g attains minimum at the point x0. In fact, all the other points, the value of g at other point are all greater than the gx0. All right, let's verify this. Okay, so let's verify. So let's verify this statement, and this is exactly what we want, right? All right. So first of all, from here, if I know this, the second derivative is always positive, right? So second derivative we know is the derivative of the first derivative. It's always positive. And then from a previous lecture, we know if the derivative of function is always positive, that means the function is strictly increasing, right? So this tells us the derivative of g is strictly increasing. All right. Okay, so then from here we know. Okay, so then let's see. Because we know the derivative of g at this point is 0. Okay, and then it says gk. So we know the g prime is strictly increasing, right? Let's copy it here. Okay, so we know this guy is strictly increasing. Okay, and because this point is 0, so we have right here we'll get this G prime will be strictly less than 0 because it's strictly increasing and this point is 0, right? Okay, and on the other side, if we look at it here, right? If we look at it here, we'll have the G prime will be strictly bigger than 0 because keep in mind, G prime is strictly increasing, right? So this point x0 is 0. So on its left-hand side will be less than 0, and on the right-hand side it will be greater than 0. Now, G prime is less than 0 tells us what? Tells the G is strictly decreasing, right? Strictly decreasing. And then the G prime is bigger than 0 implies G, the function G, right? So, okay, I know the function G is strictly increasing. All right, so that means if we look at the left-hand side of the function, okay, on the left-hand side of x0, the function strictly decreasing. So the graph look like this. So it's strictly decreasing. Okay, so that's what we have on the left-hand side. And then on the right-hand side, the function is strictly increasing, right? So, okay, so on the right-hand side, the function will strictly increasing. Now, if you combine them together, you see we exactly got what we want. Okay, so away from the point, the gx is strictly bigger than gx0, and the function attains minimum value, absolute minimum value at the point x0. And that's exactly what we want, right? So the value will be, all the values will be greater than 0, which is the gx0. So the g attains absolute minimum at the point x0, and it's strictly bigger than that. All right. Okay, so the proof of this one, so now is okay. So the other one is similar. If it's strictly less than 0, and then we'll have the g attains the maximum. So all the other values will be strictly less than g0 and g attains maximum. All right, so the proof of this will left as an exercise. It's very similar to what I did for the first one, and this you can do by yourself. All right, okay, so based on the combine all this, we have proved this concavity test. So let's quickly review this as. If I know the second derivative is positive, then I have the function is concave up. If I know the second derivative is less than 0, then I have the function is concave down. Okay. All right. So the proof of the concave down will be similar to how we prove the concave up, and that's basically what we here to prove the concave down, right? So we used this to get the concave up. Okay, all right, now let's look at some applications of this concavity test. Example 2, determine whether function fx equals x cubed, where it is concave up and where it is concave down. All right, so this is x and this is y. Okay, so from high school math, we know the graph of the cubic function is like this. So this is the graph of the cubic function. All right, so this is fx equals x cubed. All right, to determine whether concave up and concave down, we use the concavity test. All we need to do is find the second derivative, right? What's the second derivative? The second derivative, right, as we did before, if you do the first order derivative, this will be x squared. And if you do the derivative again, you just get 6x because the derivative of x squared is 2x. Okay, all right, so I get a 6x, then we'll get this one will be positive, right? If bigger than 0, when x is bigger than 0, it's less than 0 when x is less than 0. All right, okay, so then we have this part, right? So we say, okay, so then we have this part will be concave when x is bigger than 0 will be concave up, and this will from this will be concave down, right? Concave up, concave down. All right, we can say, okay, well, for this part, okay, you can start from 0. So this is concave up, and then from here to here, this will be concave down. right? Okay, so in other words, if I look at a tangent line here, the graph on that part, the graph is above it. If you just look at this part, right? If you just look at the this side, and if I look at tangent line right here, right? Okay, tangent line here, then you see, okay, on this part, the graph is below it, right? It's below it, and then you notice there's a special point. There's a special point which is 0. So 0 is the place it change concavity. Right? It changes concavity. It changes from the concave down and to concave up. And this is we call inflection point. So inflection point is x equals 0. So that's the place it changes from concave down to concave up. Or, I mean, in other examples, you might see it changes from up to down. But anyway, so it changes concavity. Concavity. All right, now let's look at example 3. Determine whether the function fx equals x times x minus 1 and x minus 2 is concave up and where is concave down. And then again, we need to determine the point of inflection. All right, okay, again, all we need to do is find the second derivative, right? All right, so first, let's write this fx out. So this is x. I will calculate x minus 1 times minus 2. So this is x squared minus 3x and plus 2. And then write out with x cubed minus x 3x squared and plus 2x. Okay, let's compute a second derivative. The first derivative of this will be 3x squared minus 6x and plus 2, right? And then I take the derivative again. This will be 6x minus 6, which is 6 times x minus 1. Right? It's 6 times x minus 1. Okay, so then it's clear from here we will get when x is bigger than 1, this function will be concave up. Okay, so this will be concave up. And when x is less than 1, the function will be concave down. Right? Okay, because then this will be the f double prime, this will be bigger than 0. Okay, so we have here the double prime bigger than 0, and here double prime will be less than 0. All right, and obviously the x equals 1, because when x equals 1, x equals to 1 is the inflection point, because the function changed from down to up. Okay, let's draw the graph, right? So that we have a better view of how it behaves. This is x. Okay. All right. Now, first of all, we notice the function has 3 roots. One is 1, and the other one is 2, right? Okay, and the function. So this is x, and this is y, and 1 is the inflection point. When it's less than 1, the function is concave up, the concave down, right? So the function is concave down. So that's what the function is. It's concave down, right? Okay. And then hold on. And let's draw it, because it's 0 at 1, so it's concave down when it's less than 1. Then it's concave up when it's bigger than 1, right? So it's concave up, it's bigger than 1, and that's what we have. All right, so this is the graph. Okay, so this part is concave down, and then we have this part F1. This is concave up. Okay? So you can see if you draw a tangent line here for this portion is below 8. So if I draw a tangent line here for this portion is above 8. Right? It's above 8. Okay. Now let's do the function fx equals x times fx. Again, we want to do the same thing. We want to determine where it's concave up, where it's concave down. and then we find the point of inflection. All right, so we take the second derivative. So we do the first derivative, it'll be x and ex by the chain rule, by the product rule, then plus ex, and then the second derivative, more space. Okay, the second derivative of this, you just get this x and ex and twice of ex, right? So this we just get this ex times x, x plus 2. Okay, so then it's clear. We have when x is bigger than -2, we have the second derivative positive. So this is concave up, right? So it's okay. So this is concave up. And if x is less than -2, so we have this one is less than 0. So we have this is concave down, right? With concave down. And then of course the inflection point will be x. This will be x equals 2. It equals -2, right? That's the place when it changes from concave down to concave up. All right, let's draw the graph again. Let's draw the graph to have a better view of what happens, right? Okay, this is x. Okay, let's see. All right, okay, so this is x, this is y, and here is, I say this is -2, right? Yeah, it's the origin 0. Now, when it's 0, the function 0, okay, when it's -2, it's positive, but before -2, right? So it's less than 2, it's concave down. The function is concave down, right? Okay. Okay, so then you see the function is concave. When it's -2, it's negative. And also, if you want to find more information, you see when this one equals 0, if x equals 0 implies the x equals -1, right? Okay, so from here, I can get further information. I'll get the f is increasing, is strictly increasing, right? So, okay, strictly increasing. When the x, so this one we'll just write as x plus 1 and ex, right? Then when x is bigger than -1, f is decreasing. When x strictly decreasing when x is less than -1, right? And f prime -1 equals 0. So that's the place when it attains a local minimum. Okay, right. Okay. Now you see also you will see when x goes to -infinity, this this one will goes to 0 because the exponential decay faster than the polynomial. All right, so when you combine all those information together, I can draw the graph. The graph will be like this, right? Okay, so this is concave down, and then at the point 1, we just try to have more information. So 1 and this place, right? So this is the local minimum. The function, okay, from here when it's 0 is 0, right? Okay, so then the function will be concave up. Concave up. And that's the place when it attains the minimum. All right, so then the 2, this is, right, so here we get the inflection point, right? So inflection point. All right, so the inflection point is when x is 2, and then the y will be 2 times e to the square 2. Okay, so more precisely, we should write the point, right? We should write all the coordinates as 2, and this is 2. It's -2, so it's -2, -2, so -2 e to the -2. So this is the inflection point, and here also we should write more accurately. So if I have the inflection point, so that's when x equals 1 and x equals 1, right? So this is x equals 1, and then the y will be equal to 0. So here the inflection point is right here. Okay, so this is the inflection point. So the inflection point of inflection. So this will be 1, 0. All right, so let's just make all right, so here the inflection point x 0, so y equals 0. So this is the point. right? So this is the point when change, okay, so the inflection point will be 0, 0, okay. All right, example 5, below is the graph of function. I want to determine where the function is, again, I want to determine where the function is concave up and where is concave down, and locate the inflection point. Now, when you observe this, you see, okay, if I try to see, I will find from here to here, right? So from here to here, you find the function is concave. This is concave up, right? Okay, maybe I use, hold on. All right, so from here to here, I find the function is concave up because if you draw the picture, if you draw the tangent line, right? So if you draw the tangent line, you find, okay, the graph on this portion is above it. Okay, so I find from here to here. So this part, this is from here, this I have is concave up, right? So this portion is concave up. And similarly, if I look at this portion, right, this portion, or say this portion, the function is, the graph is concave down, right? So the graph is, it's concave down in this interval. Right? In this interval, it's concave up. It's concave up. And then if I the portion, the middle portion, this portion, right, is from here to here, and then this is concave, right? So this is concave down. Okay. Obviously, you see if you draw the tangent line, it's this portion is below it. Here, if you draw the tangent line, it's above it. Now we have 2 points, right? So here we have 2 points of inflection. Okay, so now I have the 2 points inflection, right? Point of inflection. Okay. Here let's look at another geometric feature. If we have a function which is concave up, right? So this is a concave up function. So the point is, if I choose some point which is in the middle, not necessarily just some point between A and B, and then if I look at the slope of this line segment, and then I look at the slope of this line segment. Now, obviously, the line segment is this one, right? So I say, okay, so this one, hold on. The slope of the one on the left is less than the slope of the one on the right. Right? So this is another geometric feature of concave up, which is kind of clear from the graph. Here we omit the proof. And then also you see if I have concave up function, right? So, okay, so this is concave up, right? Okay, so this is A and this B. Now, if I choose to point in the between, so this is C and D, you see, if I draw the line segment connecting these 2 points, and then within this portion, this is below it, right? So this is below it. The portion of the graph between the 2 points is below the line segment connecting the 2 points, right? So that's what we put here. Okay. All right. So similarly, you have, if you look at concave down, you say, okay, if I appoint C, which is in the middle, well, somewhere between A and B, and then I look at the line segment connecting this point and the point and the end point on the left. Okay, so we have this. We have this line segment, right? We have the slope. So this one represents the slope. It's the slope of that. And then if I look at the line segment, the line connecting the point, this point, and the point on the right, right? And then again, you see, okay, so the slope of that, obviously, this one on the left is greater than one that is on the right, right? Okay, so this, you see, this is different from the concave up one. Now, then similarly, if I have a concave down function, you see, if I draw the graph, right, so okay, if I draw the graph, right, you have, this is A, and you say, okay, this is B. I have, let's say I have 2 intermediate points. This is C, and this is D. And then you see, for in this case, in the case of concave dam, if I draw the line segment connecting the 2 points, and the portion of the graph will be above it, right? So this is above the line segment connecting these two endpoints, right? So the two connecting two endpoints. Okay, all right. So these are two geometric features associated with concave up and concave down. Now let's look at a problem from past AP test. Okay, it says we have G that's twice differentiable function. This is bigger than 0, so this means the G is strictly increasing, right? So it's strictly increasing the function. The double derivative or second derivative positive, so this means G is concave up by the concavity test, right? All right, let's draw the graph roughly. Okay, so here this is X and this is Y, and here we have several points which we are care about. So it's G4, it tells us it's 12, and G5, and we want to find that it's some partial value of G6. Okay, now this is 4, this is 5, and this is 6, right? Not very accurate, but let's say it's 4, 5, 6. And the 4 we get, and this is the graph, right? So, okay, so we have the graph of the function, which is increasing and is concave up, right? It's concave up. Okay, the 4, and we say, okay, so this is the 4, and this is 5, and this is 6. Right? All right, well, what we have, this is 12, this is 18. So if I draw, maybe let me make more steep. Okay, just make it look nice. All right, so this one will be 12. Oh, hold on. So this will be 12, and this will be 18. This is y equals to gx. Okay, so the question is, all right, what is the possible value of 6? Remember, this is concave up. Okay, so this function is concave up. And for concave up, remember, if I look at there's the geometric feature. If I look at the line segment of this and the line segment of that, the slope of this is larger, right? If you look at this, the slope of the one on the right, on the left, on the right is larger. Okay, so then we have by this geometric feature, right? By this geometric feature, we know the slope, this part. This is the G5 minus G4, right? So the slope, G5 minus G4 divided by 5 and 4. This one is less, okay? So it's less than the piece on the right, which is G6 minus G5 over 6 minus 5, right? Okay, what is this? Okay, so this one will just be 6. This will be 6. So 6 are less than. We have is G6 and minus G5, which is 18, which is 18. So I get G6, the value of this guy has to be greater than 24. Now, if it's greater than 24, and then if you look at all the possible choice, we find this is the only one that that fulfills the requirement. It has to be greater than 24.